I want to talk about supersymmetry at the linear collider. After a brief introduction, I will first talk about direct search measurements that can hopefully be possible there. Then I will talk about indirect search measurements, and finally comment briefly about the complementarity of the linear collider and the LHC. When I will talk about SUSY, I will mainly focus on the minimal supersymmetric standard model, which means, simply speaking, that each standard model multiplet is enlarged to its double size, so the number of particles are doubled in the MSM, roughly, which means that here for the standard model fermions with spin 1/2, we have their superpartners with spin 0, the squarks and the sleptons. For the standard model gauge bosons with spin 1 or spin 0, we have the SUSY partners with spin 1/2. One important difference that has been mentioned by Michael, of course, is that in the MSSM we have 2 Higgs doublets and therefore 5 physical states and 3 Goldstone bosons. I will also assume CP conservation and R parity conservation. One could give one talk alone about motivation of supersymmetry. Why do we think that this is, or this might be a very good candidate? I will just very briefly mention 3 nice predictions that have turned out to be true or may be true. The top quark mass has long been predicted by guts like M. Sugra to be in the right range where it has been found experimentally. The effective mixing angle has been predicted at the right value, contrary to the standard model. And also, supersymmetry always predicted a light Higgs boson at 3 level lighter than the Z boson mass, or now lighter than around 135 GeV. And this seems to coincide, first of all, with the indirect search, also mentioned by Michael, at around 200 GeV, and maybe even with these now 2.1 sigma hints at the lab at around 115 GeV. So this all looks very nice with supersymmetry. So if we think that there is, or if we've seen something that looks somehow like supersymmetry, what should we go for? Of course, first of all, it has to be established that every partner has its superpartner. The quantum numbers have to be shown to be the same, apart from the spin, which should differ by 1/2. And the standard model and SUSY couplings should be identical up to higher order corrections. And from the SUSY masses, one should somehow infer on the SUSY breaking. And what can the linear collider do there? Well, it can provide precise measurements of masses, production cross-sections, branching ratios, angular distributions, and also precision observables. And also the question about the complementarity about Tevatron LHC is relevant here. And I will try to touch all these points in my talk. I want to give you one example about the masses appearing in supersymmetry. Very prominent sector, the stop sector, where the stop is the scalar part of the top quark. We have 2 scalar tops, stop left and stop right, which have this mass matrix here. In the diagonal, we have, besides the top quark mass, also this m stop left squared and m stop right squared, soft SUSY breaking parameters. And the matrix is not diagonal. We have here in the off-diagonal m top times xt, where xt can be further decomposed to at minus mu times cotangents beta, where at is also soft SUSY breaking parameter. And as I said, this matrix is non-diagonal. It has to be diagonalized with the angle theta stop to give these 2 mass eigenvalues, m stop 1 squared, m stop 2 squared, so that the physical parameters are the 2 stop mass and the mixing angle. But equivalently, one has 3 soft SUSY breaking parameters, m stop left, m stop right, and at. And it is obvious from this little example that the soft SUSY breaking parameters determine the SUSY mass patterns. And this actually is one of the big problems in supersymmetry, the pattern of SUSY breaking. Because in the unconstrained MSSM, you have 105 new parameters, masses, mixing angles, and phases. And this is, first of all, very hard to handle. You cannot scan over this parameter space. And it's also hard to believe that you have a theory with more than 100 independent parameters. Nobody, I think, believes this. So what are people doing? They look at a constrained MSSM. They assume some underlying theory where the SUSY breaking takes place in a hidden sector, which is then transmitted to the visible sector and gives rise to the MSSM. And this can indeed lead to a very large reduction of new parameters. And I list here only the very most prominent theories without explaining them in detail. M-SUGRA, minimal supergravity-inspired SUSY breaking, gauge-mediated SUSY breaking, anomaly-mediated SUSY breaking, minimal gaugino mediation. There are more, Shirk-Schwartz breaking, and all give rise to different patterns of SUSY breaking at low energies. Finally, I want to say what I will mean with the linear collider. Besides, of course, E plus E minus collider, I will assume that the energy range is between around 350, so the TT bar threshold, and around 1000 GeV. I will furthermore assume that polarization is available, 80% for electrons, and hopefully 60% for positrons. And I try to emphasize when measurements really rely that this polarization is possible. Furthermore, there's a good chance that there will be a low energy run called giga-Z, either in parallel to the first runs or maybe after the first runs, which could produce around 10 to the 9 Z bosons in less than 1 year, or around 10 to the 6 W plus W minus pairs. There are, of course, other modes at a linear collider, also mentioned in previous talks, the gamma-gamma mode, the gamma-E mode, or the E minus E minus mode, but I will not cover these here. And the main references for SUSY at the linear collider are the Tesla TDR, the NLC resource book from SNOMAS, or the ACFA JLC report. If I forgot any citation to one of you, you will certainly find it in here. Okay, so what is the first thing? We have to find supersymmetry, which is one of the main tasks of the Tevatron, the LHC, and also the linear collider. And as I said, the parameter space is very huge, and in order to develop all these tools that one needs and to test them, certain benchmark scenarios have been proposed. And besides the SNOMAS consensus that there should be a linear collider as the next machine, there was also consensus on which benchmark scenarios should be looked at. They were called SPS, the SNOMAS points and slopes. These are points and lines in the MSSM parameter space that should exhibit certain MSSM characteristics, and that also should fulfill, at least partially, depending on the model, other constraints like cold dark matter, branching ratio B2S gamma, or other rarity case G-2 of the muon, or precision observables. The points should be used for detailed analysis, where the slopes should show the variation within the parameter space, and maybe also show for one point how far one certain collider could go for this point. And I would like to encourage everybody who is planning to do some studies to use these SPS for future studies, and then different groups will result in comparable results, and this would be very nice and helpful. How does this look like? The SPS, we have 6 M-SUGRA scenarios, 2 GMSB scenarios, 1 AMSB scenario. We plan to cover much more: minimal gaugino mediation, N-MSSM, CP violating, R-parity violating, string inspired. We didn't find time for this, but I will show you briefly how this looks like. And everything right now should be already available at this web address, and will, of course, also appear in the SNOMAS proceedings very soon. Okay. For example, one of the 6 M-SUGRA scenarios, so-called typical point, where, of course, typical is very much your personal choice. The point is first defined by its high energy parameters here, which are then evolved by renormalization group equations to lower energies. And it has been said that EtherJet 7.58 should be the standard for this, because, of course, in the end, only the low energy parameters define your scenario. And this is how the spectrum at the electroweak scale looks like. Here the masses, and here Higgs bosons, leptons, gauge-genos, and quarks. And these two orange lines should indicate roughly the linear collider reach, here for a roughly 800 GeV collider or for 1 TeV collider. And in this example, the Higgs bosons should be all accessible, leptons should be accessible, also the gauge-genos should be accessible, only the quarks should, to a large extent, lie outside the range. But, for example, you can access here the stop 1, and you can also pair produce them, maybe stop 1 and stop 2, so even if a particle is above this line, it might be accessible. This was the typical M-Zugra scenario. We have also focus point, one point in the co-annihilation region, one with very light Higgses, one with a light scalar top, and one without gauge-geno mass unification. For GMSB, we have two scenarios, one with a Stau NLSP and one with a Neutralino NLSP. I will also show you one here. With a Stau NLSP, here again with the high energy input parameters and with the low energy masses. Again, the Higgses should be accessible, the leptons and the gauge-genos, whereas here all the quarks are outside the reach of a linear collider. Finally, one AMSB scenario. And here the situation looks a bit worse, because only the light Higgs boson should be accessible. The leptons, yes, but also only parts of the gauge-genos, and all the quarks are outside the kinematic range. And it would be very interesting to have analyses for these scenarios, for example, to disentangle all these states that are in this little area of mass range here. Yeah? It would be very nice to see whether people can really disentangle all the different masses, and these points are thought for these analyses. Okay, now what can be seen at the linear collider? What can be looked at? First, production of fermions. A plus A minus goes to either right-right, right-left, or left-left, or if they mix 1-1, 1-2, 2-2. And it's very simple to calculate all the cross-sections at tree level, but of course this is not enough. One has to do more. The linear collider precision requires much more. One needs at least one-loop corrections for the production and the decay, which is to some extent now available for scalar tops, but is to a much lesser extent available for the leptons, but it should be completed. And another thing that has to be included are, for example, finite width effects, where here E plus E minus goes to SMU plus, SMU minus, and then these decay, of course, like indicated in this Feynman diagram, and this changes significantly the production cross-section. I will show you an example in a minute. And if you have these production cross-sections, you can, or if you observe these particles, you can use this for mass determination. There are two methods. One in the continuum for the kinematical endpoints for this decay. For example, if you measure the energy spectrum of the mu's, you can then infer the masses of the LSP or the SMUons. Another method is, of course, a threshold scan, which is probably more precise. And here the finite width effects are very important. I have one example here. E plus A minus goes to SMUons, which is P wave, beta cubed. And if you look at this, here this red dashed line is the tree level production cross-section, and this solid line is what happens if you include the width of the SMUons. So if you want to perform a threshold scan, this definitely has to be taken into account to do it right. You can do the same, for example, for selectrons, where you can here flip the polarizations of the incoming electrons and positrons. So polarization is needed in order to produce different final states, or to switch on the S-channel contribution, or to have only the T-channel contribution to switch from P or S wave. And I have one more example here for the E minus option, only with a T-channel exchange with then S wave. And this looks like the following. Again, the red curve is tree level, and then the solid curve is with including the width of the selectrons, and you can again see that there's a considerable shift here, and this has to be taken into account. If you measure these production cross-sections, you can perform, or you can try to perform, a very nice test of supersymmetry. As has been said before, SUSY predicts the equality of these couplings, for example, E minus gamma, or E minus selectron and the SUSY partner of the gamma. At tree level, they should be the same. Of course, there are higher order corrections, and yeah, they've been calculated some years ago, called super oblique corrections, and people found something very interesting here. They saw that there are some non-decoupling effects of heavy particles. If you parameterize the deviation from unity of this ratio here, it goes like this, g squared, and then the 1 loop beta function of the g, and a logarithm of a heavy mass scale of particles going around here in the loop corrections, and the electroweak scale. And the claim was that there are order of 1% times logarithmic effects here, and this might give access to heavy scales. So in principle, a very interesting idea that should be pursued. However, for this, up to now, only vertex corrections have been taken into account, and it is known that at the linear collider you cannot simply measure a coupling, you can measure cross-sections. And these cross-sections include, for example, box contributions, which can be of the order 5 to 10%, so much larger than the effects that you want to measure there. And also, the separation of scales that has been assumed is not always possible, not always so easy. You have a more complex situation. So what has to be done, what should be done, we need calculations for the full cross-sections, and these can then be compared with the measured cross-sections. And then it might be possible, if the measured cross-section agrees with the prediction, then this confirms that the couplings are indeed equal in the SUSY sector and the standard model sector. And if you find more deviations there, this might give you access to higher scales. But this is only possible if really the full cross-section calculations is available. And there's really much more work to do in order to achieve the required 1% level precision. After fermions, you can also produce gauginos, where studies have been done for neutralinos and charginos. So E plus E minus goes to neutralino, or chargino. And again, the linear collider precision requires to go beyond the tree-level calculations, which are not too difficult. First, there have been fermion and fermion corrections for the production. And more recently, also the full one-loop correction for the production has been worked out and published. Where delta gives the deviation of the higher order corrected cross-section compared to the Born cross-section. And I want to draw your attention only to two of these lines here. First of all, we have here the long dashed one, where all the fermion and fermion corrections are included. This is this line here. And then the short dashed one is the complete. And you see that even these two differ by 2 to 3% or so. So in order to make a real precise measurement, you need a very precise prediction, and it's necessary to really include the full M at the one-loop level. It's not sufficient to include only the fermion and fermion loops. Also here, one has to think about finite width effects, where first preliminary studies have been done in the last year. Plus and minus, this is just one example that has been worked out. E plus and minus goes to chargino 1, chargino 2, where then the chargino 2 decays to chargino 1 to Z, and the Z furthermore decays to QQ bar. This looks like this then, where The black one here is the tree-level cross-section, and this here is then including the width of the heavier trigino. And again, here you can see a considerable shift. If you measure these masses and cross-sections, you can hope to reconstruct the fundamental parameters of the theory, and I will give you here one example for this from the trigino sector. You have this mass matrix here for the two triginos, M2, the soft SUSY breaking parameter, mu, the Higgs mixing parameter, and off-diagonal beta enters. And you need two mixing angles in order to diagonalize this matrix for the two triginos. And for one example, one can assume that the two lightest, the lightest trigino is accessible, and that also the lightest, together with the heavier one, is accessible. This would give you a measurement of the two masses and several production cross-sections, which would allow measurements in the plane of these two mixing angles. And these are the two, this is the plane of these two mixing angles, phi r and phi l. And these lines are isocontours of these production cross-sections, for example, 1, 1, with left polarized beams and with right polarized beams. And if you combine the 1, 1 and the 1, 2 measurements, you can single out the values of phi r and phi l here uniquely. So these two angles can be indeed reconstructed. And together with the mass measurements, if you have the masses and then the angles, you can re-rotate and obtain this mass matrix. And this means you can indeed reconstruct M2 and mu. And you also have a moderate sensitivity to tangents beta. However, also this analysis has some unsatisfying points. It has been done with the assumption of 100% polarization for both beams, which is certainly not achievable, and also no higher order corrections have been included yet. And it would be interesting to see how this changes when all this is done in a more correct way. It has been shown, it has been demonstrated that you can in principle do it, but if you want to really apply it to the linear collider when it's working, then you need definitely all these corrections that I mentioned here. One last example of the gaugino sector I want to show you here. Looking at the process E plus E minus goes to trigino 1 plus and minus, where then the minus 1 decays to the LSP, neutrino, and an electron, where these three graphs contribute at tree level. And you can see here the intermediate state could be either the selectron, for example, or the selectron neutrino, or the neutrino of the electron, where there's this mass relation between these two mass states. So only one of these parameters is really new. One new parameter enters. And you can then look at the forward-backward asymmetry of this decay electron. Which results in this nice plot, AFB as a function of the mass of this new parameter, the mass of the neutrino, for different masses of this electron, and the lower dark blue curve corresponds to the prediction of the MSSM. And I want to stress here that this is done for polarization, again, 80% of the electron, 6% of the positron, and it's only possible if you assume that you have positron polarization. And it's clear if you can measure this asymmetry here, you can somehow have access to the mass of this neutrino. And for one example that has been published, if you assume a measurement for here 26 plus minus 0.5%, for one mass of the electron, you can have access to the neutrino mass up to around 600 GeV, and a bit lower masses are obtained if you assume that this is really, if this is larger than 250 GeV. But The energy that has been used here was 500 GeV center of mass energy. And even if you assume that you go to 1 TeV, you couldn't reach these mass scales. But with this analysis, you can have reach to mass scales even beyond the energy of the collider. Finally, if you have reconstructed all your parameters at the electroweak scale, then of course you can try to extrapolate to the gut scale. You use your low energy mass measurements from the LHC where available and from the linear collider where available, where this is complementary, which I will show below. And you can extrapolate this to the high scales. And only one example here for the M-SUGRA case. Here for the 3 gay genome masses that are evolved to higher scales and which should meet in one point if indeed M-SUGRA is true. And of course, in this example, this was the case, so it works out. And you do the same with the squarks and the sleptons, and they also unify somehow at one point here. Unfortunately, I didn't get the plot if you have only LHC uncertainties, but then this area here blows up to nearly the whole range, and you cannot say anything anymore. So in order to perform this analysis, it's really crucial to have linear collider precision. And with this, you can really test gut models and reconstruct the fundamental parameters of the theory. I will also briefly talk now about indirect search or measurements. How does this work? It's a comparison of the precision observables with a theory. You take your precision observables, G mu minus 2, a branching ratio B to S gamma, or the classical ones, MW, or the effective mixing angle, and compare this with a prediction of your theory. And in this way, of course, you are sensitive to loop corrections that enter for virtual particles, labeled X here. And this can either improve indirect constraints on the unknown parameters that you don't know yet, or the comparison of direct and indirect data will serve as an important consistency check of your model. And in order to perform this, very high accuracy of the measurements and the theoretical predictions are needed. Yeah. Just to show how this works out nowadays already to some extent. The classical example, the W boson mass is a function of the top quark mass, where the red band here together with the blue band is the overlap between green and red. This is the standard model prediction, where this is the Higgs mass range, 113 GeV here, 400 GeV here. And the green band here together with the blue one is the M region, where here one has light supersymmetry, here one has heavy supersymmetry. And if this is compared to the measurements, looks like this. Gives you this ellipse here, which shows a slight preference to the MSSM. Of course, this will not be an issue anymore at the linear collider times, because then we will know whether we have supersymmetry or not. But if you do this then, again, this curve should lie somehow in the range predicted by the model, and this is then a consistency check. What is also already done nowadays in this respect, if you assume that supersymmetry is true, and you take the measurements of G mu minus 2, although this has become somewhat weaker over the last 1 month or so. But if you combine this with a branching ratio B to S gamma, you can already single out some SUSY parameters. You have to say that this product should be positive and this product should be negative. So this works already to some extent. This was mentioned in Michael's talk before. The best SUSY precision observable will actually be the mass of the lightest Higgs boson. We have this tree-level prediction, but as has been said, we have large Yukawa couplings here, proportional to top quark mass, and we have large corrections, therefore coming from the top stop sector, which at the one-loop level go like this, m top to the 4th over mw squared times the logarithm, and here the scalar top quark masses enter. And if you rewrite this then in terms of soft SUSY breaking parameters, they enter here at these 2 places, and then it is clear that a measurement of the Higgs masses and couplings can give you information about the soft SUSY breaking parameters, especially of the stop sector. And time is running out a bit. I will give you one example for this, where the Higgs boson mass can really be used as a precision observable in order to obtain constraints on the stop quark parameter, on the stop parameters, and also the mass of the CP odd A boson and tangents beta. And this is a combination of direct and indirect constraints. And it works like the following. First, you take your direct information. You look at the reaction. E plus, E minus goes to stop 1 at the linear collider. And again, you need beam polarization, 80% electron, 6% positron polarization. And if you flip the polarizations, you can very precisely measure the mass of the lighter stop quark, which is supposed to be accessible, and also the mixing angle of the stop sector. You get a very precise determination of these. This is the direct information you can obtain. And this has to be compared with the indirect constraints, where I now assume a precise measurement of the Higgs boson mass, which can hopefully be measured to about 50 MeV. But this is dominated by the theoretical error, which we hope to press down in the next 5 to 10 years to about 0.5 GeV, where it's now around 3 GeV. This will be a lot of work to do. And also one assumes here a measurement of the W boson mass of 7 MeV and the effective mixing angle of around 1 times 10 to the minus 5, both performed at GZ, where the Higgs mass, of course, measured at the linear collider itself. And if you make these three assumptions for these measurements, and you look at the parameter space again of the mixing angle and the heavy scalar top quark mass, you can single out a certain region of parameter space. Blue is LHC region, green is the linear collider region, and red is the GZ region here. And if you now impose the other constraint that you have already measured, this mixing angle, it looks like this. You can single out a very precise indirect determination of the heavier stop quark mass at the 5% level. Either you found the heavier scalar top, then you can compare this and see whether your theory is consistent, or the heavy scalar top quark might not easily be accessible at the LHC, and this value is also probably outside the reach of the linear collider. Then you have at least an indirect measurement of this important mass scale. And I want to emphasize this once more. The SUSY particles and also the light Higgs boson will hopefully be measurable at the linear collider, and the linear collider will provide certainly very high accuracy measurements. But these high accuracy measurements are only meaningful if they are matched with also the theoretical predictions at the same level of accuracy. This means mass predictions at the 1% level, production and decay predictions at the 1% level, and Higgs mass predictions at this level here, about 200 and 500 MeV. But this means that for many processes, still a factor of 3 to 10 improvement in the uncertainty from unknown higher order corrections is needed. And this means that a lot of calculational effort is needed, and we should work on this now and continuously till the linear collider will hopefully start. And therefore, theoretical calculation should always be viewed as an essential part of all future high energy physics programs. Finally, this will not take long, complementarity of linear collider and LHC. Mass range, the situation is pretty clear. The LHC, of course, has a much higher mass reach for the squarks and the gluinos compared to the linear collider here. For the sleptons, the linear collider has some advantage, has a higher mass reach for the sleptons, also for the gauginos, even more pronounced. So they are kind of complementary here. If you look at the precision in the mass measurements, of course, only here if these particles are accessible, then the linear collider always has a big advantage compared to the LHC. And as I've shown you before, this is really necessary in order to, for example, reconstruct the gut scale. On the other hand, the linear collider can indeed help to make the LHC mass determinations better, because the main source for the LHC uncertainties is the uncertainty in the LSP, which is assumed again at the, 5 to 10 GeV level. And at the linear collider, you may be able to determine the mass of the LSP down to the 0.1 or 1 GeV level. And this here is a plot from the Atlas TDR about the correlation of the masses of the second lightest neutralino and the lightest neutralino, the LSP. This is the correlation here. And you can see if you have a determination at the 10 or 10% level, this translates into a large uncertainty also for this mass here. But if you assume that you can measure this down to about 1 GeV, then you can single out, or you can measure these, the mass of the second lightest neutralino to a much higher precision, and 2% should be possible. So here, the linear collider can really help the LHC. The second example, which works in the same way, is for the mass of the scalar electron. Again, this is the correlation. And if you apply the linear collider mass determination here, also the mass of the selectron should be measurable down to the 2% level. And this is indeed applicable to all LHC mass measurements, but unfortunately has not been worked out yet in detail, or no simulations have been done for this. And it is planned that how the linear collider can help or could help the LHC, or maybe also the other way around. This is planned to be a topic at the next European Linear Collider workshop in Saint-Malo in France. And I think the organizers would be very happy if some input would come here. So if everybody of you has a nice idea or want to contribute, just contact them. Of course, there are many things that the linear collider can do better. I just want to list them here. If particles are in the kinematic reach, the linear collider is much better in the determination of the spin and the quantum numbers, measurement of probably CP violating phases, the mixing angles, the mixing parameters of the gauge genos. Model-independent determinations of SUSY parameters can be done in a much better way for the LHC. The model assumptions play a much stronger role. You can more easily distinguish between the left and right-handed slaptons, where, of course, polarization of the beams is then necessary. You can perform a much better measurement of the branching ratios of SUSY particles, and also for the determination of tangent beta, the linear collider is far superior. I conclude. The main task is, at all the future colliders or current colliders, establish supersymmetry, which means measurement of masses, quantum numbers, and so on. In order to perform analysis in this direction, new benchmark scenarios have been proposed, the SPS, no mass points and slopes. And we have here 6 M-SUGRA, 2 GMSB, and 1 AMSB scenario that I presented. If you look at fermion production, full one-loop corrections are necessary and partially available. Finite width effects are meanwhile taken into account, which is necessary. And if you do all this, then you may be able to infer something about the pattern of SUSY breaking here. Gauge geno production, the same. Also, full one-loop at least is necessary. Finite width effects have to be taken into account, which is partially done. And this may help you then to reconstruct the fundamental parameters of the theory, like I've shown for the Charge-Geno sector. And if you do this here, you can try to reconstruct also the gut scale, where really the linear collider precision is necessary. If you look at the indirect determination or indirect measurements of supersymmetry, the mass of the lightest Higgs boson itself is the very best precision observable. And I've shown you a nice example where you have sensitivity to the heavier scalar top quark with the giga-Z precision. Finally, the linear collider is certainly complementary to the LHC, and it might help to improve the mass determination at the LHC. But all in all, a lot of work still has to be done. Thank you very much.
Sven, thank you very much for that excellent talk. I think your subtle point about the importance of precision theoretical calculations has been noted. Are there any questions? We have time for just a couple of questions before we break for lunch. Yes?
I just want to make a point about these works. I mean, when you show these SUSY spectra, quite often these higher states are very degenerate. It's not clear that the LHC can actually separate those. That might form the basis of an argument for very high energy.
You're certainly right.
Could you repeat the comment?
Oh, sure. It was mentioned that, I can show it again. He was referring to the mass spectra for example, here, just one example, AMSB scenario. The heavier masses in the squark sector are often very degenerate. They are lying around here, and it's not clear whether the LHC can actually determine all these masses. And he emphasized that this might give more emphasis to an even higher linear collider, plus or minus linear collider. This is certainly correct. Yeah, nobody thinks that we should stop there. Yeah, that we should stop at 500 or even 1,000 GeV. But I think the case is also clear that with the energy that will hopefully be available, you can already see a lot of things. But why shouldn't we go in 10 or 20 years to higher energies? Yeah, of course.
Thank you for that comment. Any other questions or comments? I can't see any. If not, let's thank both Sven and Michael for their excellent talks.